Hello students. In this session we are going to learn about hidden Markov model techniques. So till now for indexing and searching purpose we have seen other techniques. So in this model we are going to learn about hidden Markov. So what is meant by hidden Markov models, how it is going to work, and these are basically used for searching the text. Okay. So how we have done in the previous example, we created one data structures. Here you will have the document. Okay, and what is the key you are going to search and whatever the related data structure you are going to create in a hierarchical manner. It may be a tree structure or anything else. So coming to here, you are directly using your textual data, and in the previous example we used query as a document, and in order to find the similar document it. For example, in a Google server you are typing some word called kill. Kill is a query now. So it will check for in all other document available in this whether this kill is a query is found or not. So this we have done with this. So similar to it, we will also write one query in this model and you will search whether it is available in your document or not. So in this example in HMMs, we are going to take the data from unknown statistical processes which are equivalent to required the set of queries and which are relevant to that particular document. See what we have done in the given variables in the previous example. If you have computer, so whatever the related letters you are storing in the document 1, document 2, like that we have stored. But in this hidden Markov model, we will not use any statistical process. We will directly incorporate without knowing the previous information about your data which is already stored. And another way is you can use, you have to remember that whatever the document it is relevant, we have to consider the document. And we can also use state transitions. So what are state transitions? One second. Yeah. If you are, see we have seen in the flat formal automata. So you will have the states, you will move the states on A, on B. So this is Q1, this is Q2 and another this is your final state. So similarly, either you can go for the unknown statistical process or you can create one state transition through the noisy channel, like whatever the states, whatever the documents you are going to use, these documents have to be stored as a transitions. Okay. So this can be viewed and you can easily identify the relevant one for your search. So what we have observed in this model, so whatever you are generating the keys, unknown keys, because I don't know whatever the key I am typing over here. So just according to the transitions or relevancy you are checking the documents and you are giving the output. So whenever you are getting unknown keys, you are getting the data with the relevant values, but in the noisy channel sometimes there may be a mismatch. So in the author's way of expressing ideas and specific query. So for this I want to give an example. For example, we are writing, I'll write as quadratic. So what is the context of quadratic I am using in this particular key element? So the view of author is different and view of search, who is the search element, it is different. So it may be different in both the cases. Okay. So this have to be checked whether the idea of expressing the user's ability to specify his query, because if I am mentioning this one, I should be very keen and clear explanation in order to get the data, because we are taking the data warehouses where complete dump of data will be there. So which cannot be a single part or which cannot be in the single context. So in that case, whenever you are working with the noisy channel, you will have more unrelevant data than relevant data. So in that case, your hidden Markov model will be working efficiently considered to other models. So these are the persons who have worked on this So Leek, Miller and Sejwas, who have given that D is a relevant document and Q was the query. So you have to produce a query like this. So what is P of D? P of D equal to R by Q. R implies your relevancy and Q implies your query. And what is the probability of getting the relevant document according to the query? You can apply the Bayes rule. So we have know the Bayes rule. So hidden Markov model, what it is going to do? It is using the formula P of D equal to R by Q with the help of Bayes algorithm or Bayes model. So this is the exact thing who have proposed by Leek, Miller and Squats. So what is the biggest problem when you are working with this approach? So it is to estimate the transition probability matrix, because whenever I am talking P of D equal to R by Q, so I have to calculate relevancy for each and every query what I am taking. So when we are mapping this particular matrix, it will be very difficult, okay? And you are talking about the corpus. So corpus means, imagine in your database how much corpus will be there. So if I take this one, how much text data will be there? Okay, so when you are doing this, if you have 1000 words, for example, I am telling, so you have to map this particular value for each and every word in that, and this can be done using this particular formula. Okay, so P of Q by D is R, D means document, P of D is R by P of Q. So this matrix have to be calculated for each and every corpus present in your document. So what we are going to do after calculating? So after this, you have to calculate a byproduct for similarity measures, which can be ranking the output. For example, so after this, you have to check with the ranking algorithms in order to get the complete rank of the value. Before that, you have to calculate P by Q, R by Q value, and you have to add the weightage. Okay, so till here, R by Q comes under HMM. So after that, you have to enter into the ranking algorithm. So this is independent of that, but you can continue with the HMM by after that you can go with the ranking part. Okay, so now we'll see what is the advantage of ranking over here. So whenever you are getting the complete query, so whatever you are getting the output, for example, I have calculated the matrix for each and every value. So for each and every value, I have calculated the matrix. For example, we have seen in the example C1, C2, C3 corpus 1, and what is the relevancy of this R1, R2 and R3. Suppose I am getting 2, 3, 4, 6, 7, 8, 0, 1, 1. Okay. So whenever you are doing the ranking purpose, so you will do in the ascending order. So what happens, or descending order? 8, 7, 6, 4, 3, 2, 1, 0. So this ranking will tell that 8 is having the highest relevancy when compared to all other items. Similarly, we will go in this order for use. So what happens, whenever you are taking 8 as a relevancy document, what happens, your precision will increase, right? So end of the day, we want more precision and we should get more relevant data for that. And most of the likely items can be satisfied with the least likely rules. Okay, least likely items here is, so when I do the ranking part, what I'll do? I'll get in this way, 8, 4, 3, 2, 0. So I will eliminate these two and I'll only accept these 4 values, right? So this will be, least likely items will be identified according to this query, and this will reduce the overhead by allowing the user to display the most likely relevant elements. So when I do this, I'll automatically ignore these values and I'll mention these 2 things. So when I go for 8, if I'm covering the complete query, what I'll do? I will use the complete thing. After that, if I go for 4, it is covering all this plus or minus this, I can ignore these values. So this is the advantage of the ranking part. So we will remove the least likely items and you go with the most likely items according to the ranking. Now what is the another system is, we started from Boolean system. You remember we have given weights for each and every value. Weight will be 0 or 1. 1 means it is more relevant. Okay, 1 means which is more relevant and 0 means not relevant. So if you are getting more ones, again you have to do ranking part, and according to the ranking you can do that. So this is the relevance of the each and every user statement. And what we can do is, whenever you are searching for the opposite or different corpus, you can use a ranking algorithm, and this has become more in feature of the modern system. For example, yeah, I'll give you one simple example for this. Suppose I have opened your Google. So I am clicking on ranking. See, remember, it will open one different web page, and you have so many links for that. How this one is getting at the top level? Okay, so when you think of in this manner, this ranking is more. Okay, so ranking is high. After that, which is comes under this one, then this one. So if you go down or if you click here more pages, 1, 2, 3, you will have this arrow, you click on next, you will get more web pages where you will have the same similar data related to this. So how these are ranked over here is using your ranking algorithms. Okay, so I feel that whenever I am getting the topmost one, usually we'll go with the topmost one, because I'll feel that this is more relevant to my search document, right? So after that, the relevance will be decreased and decreased. Sometimes if you go down completely, you may get unrelevant data also. So it depends upon how much efficient you are giving the query. Okay, so this is the advantage of the ranking, one use case also. Now, according to the summary, so Belkin and Croft, so he gave the relevance feedback. Okay, so who will give the relevance feedback for the given values? Ranking algorithms will give the relevance feedback, and relevance feedback was published by Rocchio in 1971. He was he documented all the experiments by rewriting the query times. What you have done in your query, each and every term, again recalculated the weight. According to that, ranking has been done, and it is represented in the form of vector. Okay, so it is represented in the form of vector. Suppose if I take R1, R2, R3. So 3, 2, 1. So ranking high will be R1, ranking next level, third level. Okay, so it depends upon the queries and items in order to represent the ranking of each query and item. So this concept was found according to the probabilistic model by Robertson. So previously he was taking the relevancy according to the weightage, and this guy started working on the probabilistic model, where he presented what is the probability of this particular ranking element in your vector. Okay, so how you are going to calculate the weight of that particular vector, what is the formula we are going to use. Okay, so according to this, you will have many queries. So you can also modify old query to the increased weight. How you can do that? Okay, so whenever I am browsing more elements, whenever I am browsing more documents, what happens? You will get more relevant data sometimes. And what is the probability of getting more relevant data while going with the more documents? So this is a formula where you'll have the, okay, so you'll have the R. QR is a revised vector. This is the original query. R is the number of relevant items. DRI is the vectors of the relevant items. This is non-relevant items. DNR is the vectors for the non-relevant items. So by calculating this particular formula, you can change old query to revised query. Why we are doing this? In order to increase the relevance, right? Increase the relevance. Okay, and again this is also one more formula where you can adjust the weight of the all values, where you are introducing a constant value, where you can use this alpha. Alpha is your weight adjustment factor. Okay, so by using this formula, you can create a new query coming over the old query. So according to the example, okay, one second, before this I want to show you one figure, then we'll come back here. Yeah, so if you see here, you have the positive feedback and negative feedback. So impact of the relevance feedback. So when you take this, all these are values. So this is your positive feedback where you'll have this particular item will be outside. When you take this one, this black color will be inside. So that is a feedback process of positive and negative feedback. Yeah. So if you see the explanation, the filled circle will be non-relevant items, and the circle will represent the relevant, and oval will represent the items that are returned from the query, and solid box is the logical where the query is initially, hollow box is the query modified. Done. Okay. So according to that, you have to check relevancy and non-relevancy factors. So these are relevant, these are non-relevant. So these are, one second. So if you take the documents, inside the circle are relevant, outside these are non-relevant. Okay. So this is your modified, this is your not modified previous query. So I hope this is clear. So in the next session, we are going to learn about more algorithms. Thank you.